This is number 53 from chapter 20. The drawing shows a circuit that contains a battery, two resistors, and a switch. What is the equivalent resistance of the circuit when the switch is A, open, and B, closed? And what is the total power delivered to the resistors when the switch is C, open, and D, closed? Alright, well, to start this problem off, I actually drew the same picture that was in the book. Here are our two resistors in parallel, and here is our switch. And it alternates between being open or closed. And here I actually wrote down all of the given variables in this problem. R1 being 65 Hertz, R2 96 Hertz, our voltage is 9 volts. And these are the two equations we'll be needing: the power equation, which is current times voltage, and Ohm's law, which is voltage equals current times resistance. Well, part A asks for the equivalent resistance when the switch is open. So when the switch is open, the current's going to come through here, going to go around and go down the first resistor, but that's it. So in part A, our equivalent resistance would simply be the value of R1, which is 65 ohms. Part B asks for the equivalent resistance when the trap here is closed. So when the trap is closed, current is going to go through here, some's going to go down R1, and the rest of it's going to continue over to R2. So we use the equivalent resistance equation when resistors are in parallel, which is 1 over Rp equals 1 over R1 plus 1 over R2. And what we do is just add these, we do calculate these and take their inverse value to get the resistance in parallel, and you get a resistance, an equivalent resistance of 38.7 ohms. And then part C asks for the power delivered when part C asks for the total power delivered to the resistors when the switch is open and closed. Part C is open, so first thing we have to do is solve for our current. So we use Ohm's law, which states the voltage equals current times resistance. So part A, we see here that we have our resistance RA as to reference part A in the problem, times the current would give us a voltage. Since we're solving for our current, we know that we could manipulate this equation, so it's voltage over our resistance. We get a current of 0.138 amps in part A. And then to simply solve for our power, the power delivered, we use the power equation, which is power equals current times voltage, and we just plug in our values, our current being what we just solved for, and our voltage being was given in the beginning of the problem, and we get a power of 1.25 watts in part A. And in part D, I ask for the power delivered when the trap here is closed, and we pretty much do the same process, only we're using our equivalent resistance of two resistors in parallel, like we did in part B. So we got V equals IRV. We're still solving for our current again, so our current is going to be all voltage over our equivalent resistance of our two resistors in parallel, and we get a current of 2.33 amps. And do the same thing we did in part C, and we're going to solve for our power by multiplying our new current and our voltage, which is given to us in the beginning of the problem, for a power of 2.1 watts.